Okay. Hey everyone. I want to talk about this blog post I wrote yesterday, modeling and proving logic gates in Coq. So I've got some feedback saying like it's very hard to read. So I thought, okay, let's do a video format. Yeah, basically in this video I'll be going over what I wrote in this blog post, basically like how to model and prove the properties of logic gates. Um, to follow along, like you have to go to this website, like this online Coq interpreter. So yeah, click on this button and you will get a clean slate. Let's wait for it to load. So basically, what I wrote in this is like a bit of a bit about what Coq is, and then what is AND gate, OR gate, and the primitive gates, and then like how we can model it in Coq. And once we are done modeling it, like let's prove the properties of it. Like say for example, so this expression should be equaling to this, things like that. So yeah, it's still loading. Let's wait for a few minutes. I don't know why it's taking. Yeah, the standard library is a bit heavy, so okay. For those of you who don't know about Coq, spelled COQ, it's a like formal theorem prover. Like mathematicians use this tool to prove theorems. You might ask, why? Okay, basically Coq is a functional language, and you might ask why another language? Why not prove those theorems in an existing language like Python or JavaScript, right? So you might be heard about this thing called halting problems. Basically, you write a program and you try to execute it, and it keeps on executing. It doesn't stop. Basically, it doesn't halt, right? So there are some theorems. If you write it in a regular like imperative languages, it doesn't stop. So that's where Coq comes in. It's specifically designed to solve theorems, and it will halt. So I'm not going to go into the details of those things because even I'm not familiar with those stuffs. So I'm learning it out of curiosity. So yeah, let's start. So basically, uh, I'll model. I'll be going over the NOT gate. So I'll model the NOT gate, and then I'll prove the property of the NOT gate, right? So yeah. So I'm not gonna write it, like I'm gonna copy paste it. So this is the modeling. I'll go over it. Uh, So basically what this says is like this definition keyword is like and is a function which takes in two arguments a and b, which is of type boolean, and this function returns a boolean. Inside the body of the function we have this match statement, which is nothing but doing pattern matching, right? It doing pattern matching on a. It checks on the first match, it checks whether a is true. If that is it's true, it's gonna return b. In the second case, it checks for false. If that's the case, it's going to return false. So that's what this definition is. In imperative languages, you might call it, not you might, you will call it as like functions or procedures. So that is what this definition is. It's just a function that accepts two arguments and return something. In this case, boolean. Now let's verify whether this works or not. You can do this by this compute vernacular. So in Coq, this compute, this definition, anything that starts with a capital letter is called a vernacular. That's how a Coq program starts. So you can do compute and pass in two arguments of type boolean. Let's say true and true. It should return true. For all the other cases, it should return false. As you can see here, I'm ending this statement or a command with the dot, otherwise the Coq will throw us an error like expected after this. So you should always, it's like a semicolon kind of a thing. Yeah. So in other cases it should return false, 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 true, is true. now that we have modeled the AND gate, we can now prove it. So for proving it, we need to write a theorem, right? So a theorem, what a theorem is like it states something and it gives you the hypothesis, and you can use the hypothesis to prove that statement. So here, let me find that theorem for AND gate. Yeah, this is the theorem. Let's see. So yeah, so this is the theorem. You may notice like you can see that I've executed this line, and then in this section, the goals section, it tells me like there is one goal that we need to prove. Let's go over this, what this goal is. So this is you might notice this symbol. This is called for all. So it's spelled for all. You can see Coq turned it into this mathematical symbol or notation, right? So how to read this is, for all BC, which is of type Boolean, B and C is equal to C and B. So basically this one. If we compute AND for B and C, it should equal to AND CB. Basically we're flipping the arguments to the AND gate, right? So this is what the theorem is. We have to prove this. Let's do it. So everything will start whenever you're starting to write the proof. You start with this proof vernacular, and in Coq, you're gonna whenever you start proving theorems, as you can see here, like there's this horizontal line. Below this line, like you have the goal, and the goal states like we have two variables, right? So which is of type Boolean. So if you think about AND gate, like there are four possible cases, right? True, 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 false, false, true, and false, false. And since B and C are like of type Boolean, we should be replacing B and C with true, false, all those stuff, right? So for that, like we have to bring in the variables into context. To do that, we can use a tactic named intros. So what this intros tactic does is, right now like I'm only writing intros. You can explicitly say tell Coq to bring in the whatever variables you want into context, so that you can use or modify those variables to prove your theorem, right? Let's stick to this. As you can see here, it brings in the B and C variables into our context so that we can use it, right? The next step is to, as I already told, we need to replace B and C with true and false, right? Let's first replace B with true and false. To do that, we can use another tactic called destruct. So destruct is basically we use it to do case analysis. What I mean by case analysis is, in this case, B is of type Boolean, right? So there are two cases. One is B is true and the other one is B is false. Similarly to C, when we do case analysis on C, there are two cases, when C is true and C is false. So that is what case analysis is. Like we use destruct tactic to do it. Let's destruct B first and see what happens. As you can see, when after executing it, B is removed from this context, only C is there, because we have replaced B with true and false. Since there are two cases, now we have two subgoals. Initially we got only one subgoal, now we have two subgoals. Similarly, we can destruct C and see how it goes. Destruct C. As you can see, like I've destructed both B and C as well. Now that if you notice, initially when we destructed B, we only got two goals, right? We have basically replaced B with true and false. But when I executed this command, destruct C, the first three got replaced with true, but the second case for false case, like it doesn't got replaced. Why that? We can fix that by doing this. See, Now that this sign is right, this is basically to break down our goals into different sub goals, right? So that is what this hyphen sign or like the minus sign is used for. So we have destructed B and C. Basically, we have replaced B with true and false cases. Did the same for C, like replaced it with true and false cases. Now that we have this two goals, we can start to prove this. As you can see, like these are two sub goals, not the primary goal, because like we have break down the primary goal into two different things. So we are now gonna solve this sub goal. You can do that by doing plus. If I do plus, so plus is used to focus on particular goal. As you can see, if I remove it, there are two goals. If I execute this plus, we are focusing on only two goals, right? I mean, not only focusing on only one goal. Yeah, now we can solve this. Basically what this says is true and true is equal to true and true. We need to basically, whenever we have a statement like this or like an expression like this, we first try to simplify the expression and see what it does, right? So in this case, we have replaced all the variables with the values we want. Basically, we have replaced B and C with true. Here B and C is true true, here C and B is true true. We can basically simplify this. To simplify this, we can use the simple tactic, and it basically it does AND operations on the left hand side. So true and true should return true. In the same goes here as well. True and true should return true. So when I execute this, true is equals true. Now we got true is equals true. Now we have to prove this equality. To prove the equality, we can use another tactic called reflexivity. So what this reflexivity does is it takes in the LHS and takes in the RHS and checks if both are same. In this case, true on the LHS it's true and the RHS it's true, so both are same. So it should finish or prove our goal. If I execute this, you can see that this subproof is complete, but there are some unfocused goals. Focus next goal with the bullet plus, right? So basically what this reflexivity does is it proves or sub goal. It checks for equality and this is equal, so it finishes it and it asks us to focus on the next goal, and we can do that by doing plus. It also tells us focus next goal with bullet. So let's do that. So the same goes for here as well. We have replaced all the variables. We've only got true and false and true. Let's simplify this and see what happens. So when I execute this simple tactic, it should give me false and false. So false equals false. Yeah. Now let's check for the equality. It should be same. Yeah. Now we have completed two sub goals. One is for true and false, and the other false and false. Right? False and true. Now we have two more remaining, which are the same. Basically, false equals false, false equals false. Let's see that. We can focus on our next sub goal with negative or hyphen or whatever you call it. Yep. Now you can see we got only one goal, and we have C in the context. We have to replace C with true and false. How to do that? It's very simple. Whenever you wanna do case analysis on something, you can use the destruct tactic like we used here. Destruct C, and what it does is it replaces C with true and C with false. Now we have got two sub goals. Now let's focus on the first sub goal. To focus on the first sub goal, we have to use this plus. Only focus on the first sub goal. Simplify it. When I execute this command, it should return me false equals false, because false and true is false, true and false is false as well. So when I execute simple false equals false, to check the equality, you can use reflexivity. Boom. The same. Let's focus on the next one. False equals false. It should return false equals false. Simple reflexivity. And tada! We have got no more goals left, which means we have successfully proved the theorem that we have stated here. So and BC is equal to and CB. We have successfully proved it. Once we have completed our goal, we should end the theorem with QED. Otherwise, if you type some other theorem here and try to execute it, it won't, because we have ended our theorem here. So you should use QED to end our theorem. So basically in this theorem what we have proved is true is equals true false is equal false, and the same couple more time. And if you, what you can see from here is this is what AND is. If you look at the truth table for AND, I'll show you. So basically there is only one true and the remaining all the three are false, and basically only one true, all the three are false. Basically we have proved this using cock. I hope you've got some understanding of what cock is and like what it can do. You can use the same approach to prove the property of the OR gate. I haven't proved it in this blog because it was already too long, so I don't wanna add it. So yeah, you can basically prove the same thing here, like OR BC or CV. So you can try to prove it and see how that goes. Yeah, so that's basically it. That's I just wanted to make this video explaining what I was doing in this blog post. Yeah, that's all. Thanks.